Okay. Hi, for people who don't know me, I'm Esther Klabbers. I work at ReachSpeaker, and I'm the session chair for this session. And our first speaker today, I need to figure out how to get the program on here, is Tamás again. And yeah, maybe you can figure it out.
Okay, thank you. Hello, everyone. I am Tamás Csapó from the Budapest University of Technology and Economics, and this work is a collaboration between a couple of other universities with the University of Szeged, the Lingual Articulation Research Group, and the Research Group on Artificial Intelligence, and also Eötvös Loránd University. So similarly to the morning presentation, I will talk about text, speech, and ultrasound, but now from a different perspective. First of all, speech synthesis from text. There are well-established methods for that. So like various machine learning techniques have been used, either Markov models, deep neural networks, there are neural vocoders, end-to-end systems. So nowadays, TTS is, it can achieve a very high quality final speech output. But on the other hand, there is a topic of speech synthesis from articulation, which is also called as articulatory to acoustic mapping. So here the idea is slightly different. And the first experiment were around the early 2000s. And also it's a quite active research field. Nowadays, there are many research groups across the world who are working in this topic. There are a couple of relevant papers in the literature, like about text-to-speech systems, which are extended with articulatory information, like by Ling and his colleagues and Cao and his colleagues. They integrated electromagnetic articulography-based features into hidden Markov model-based speech synthesis. And they have shown that if in the target of the mapping, there is also articulatory information, then it might be useful also for the naturalness of the synthesized speech. So the topic of articulatory acoustic mapping has the idea that we would like to synthesize speech directly from the articulatory input. It has a potential application called silent speech interface, which has the idea that we could have an application in the long term that can record the soundless articulatory movement. And from this, it could synthesize speech while the subject is actually not producing any sound. Like as if I'm talking silently, I'm moving my lips, I'm moving my tongue, but without articulation, and some device could convert this to speech. For articulatory acquisition techniques, a couple of solutions have been used with various groups like ultrasound, electromagnetic articulography, permanent magnetic articulography, surface electromyography or MRI, lip video, and also this can be combined to have a multimodal input. So ultrasound is a solution which has a relatively good temporal and spatial resolution. And what is important to know that it's a grayscale video where the tongue is visible. I will show a Hungarian sample for an ultrasound recording.
Most a kuka meg a kuka volt.
So you can see that the tongue surface is here. And depending on the actual orientation of the transducer, sometimes the tongue is fully visible, sometimes some parts are not fully visible. I will play the video again.
Most a kuka meg a kuka volt.
In the field of articulatory to acoustic mapping using ultrasound, a deep neural network, we had a couple of previous studies. Actually, the first study was at Interspeech 2016 by a French group, and they applied ultrasound and lip to singing voice conversion. And after that, starting from next Interspeech, we also developed our methods for ultrasound to spectrum, ultrasound to fundamental frequency prediction. Also, we tried multitask training to predict ultrasound to spectrum and text at the same time with the same neural network. And more recently, we also applied like neural vocoders for the same purpose. So there is a slow progress in this field. The current study is extending these previous ultrasound-based articulatory to mapping methods, but here the idea is slightly different. So there is a text-to-speech synthesis, articulatory to speech synthesis, and the question is whether it helps if we add articulatory information to the text input. So if we combine text and articulation as the input of like a TTS system. For data, we were using the Ultrasound repository, which is a bunch of recordings from English speakers. And we were using 4 male and 4 female speakers, roughly 200 sentences from each of them. And we were using the raw ultrasound data for this study as well. It was, the ultrasound was represented as principal component analysis, similarly to the morning presentation. And so the difference between the previous study is that now the idea is that ultrasound images are the input of the deep neural network, and the target is synthesized speech. And the question is whether this information can help at all. We were using the Merlin framework for the deep neural network training. The text was as linguistic features and the ultrasound as this principal component analysis representation. For the target, we used the word vocoder. And this time we only trained the acoustic model and the durations were not modeled. We had a simple deep neural network with 6 layers, 1000 neurons, and we trained speaker-specific models. Also, we had 2 baseline systems. One of them was text-to-speech with the same data, and also ultrasound to speech with the articulatory data itself. So this is basically articulatory to acoustic mapping without the textual information. And we did it in a way in the Merlin framework, which is basically for text-to-speech synthesis, that the linguistic features were replaced with an empty decision tree to make sure that the text information is not in the training. I have a couple of demonstration samples here. So these are English sentences, and first I will play the original recording from a female speaker.
I leave it to nobody, said Shakespeare sulkily.
Now the one which is synthesized from the ultrasound to speech. After the text to speech.
I leave it to nobody, said Shakespeare sulkily.
And now when the text and the ultrasound information is both the input.
I leave it to nobody, said Shakespeare sulkily.
So if you listen to the samples, it is clear that the ultrasound to WAV, it is very hard to understand. So that the articulatory information seems to be quite few. Text to speech works quite well, even with this limited database of like 200 sentences. And there is a slight improvement when combining text and ultrasound. I will also play samples from a male speaker.
Your Captain Nemo, the devil take him, has just made us a very pleasant proposition.
This was the original recording. Now, articulatory to acoustic mapping with ultrasound.
Your Captain Nemo, the devil take him, has just made us a very pleasant proposition.
Text to speech.
Your Captain Nemo, the devil take him, has just made us a very pleasant proposition.
And now text and ultrasound to speech.
Your Captain Nemo, the devil, take him, has just made us a very pleasant proposition.
Okay, so these were a couple of demonstration examples. We did an objective evaluation with Merck-Capstral distortion. And in general, the lower values are better. And the wrongest or weakest system is the ultrasound to speech, after the text to speech. And there is a slight improvement for text and ultrasound to speech. Also, similar tendencies are found with the excitation-related features of the vocoder, like word has the band aperiodicity and also F0 for the excitation. For the F0, the results are less straightforward. So some speakers, surprisingly, the correlation with F0 in case of the articulation to speech is higher than the text to speech. And also we had a couple of previous studies when we predicted F0 from ultrasound input, and it seems to work, but it's still difficult to figure out why we can predict F0 from the ultrasound tongue movement itself. So the problem is that when we check the spectral distortions, we found that there are very strong speaker differences, and we couldn't really figure out what can be the reason for that. But in a previous study on last interspeech, we figured out that the transducer positioning has a very strong effect on the way of these recordings. So for this, I will tell a few words about how this data is recorded. When we are recording the ultrasound and speech, usually there is some kind of headset used in order to fix the transducer. This can be a headset or a metal headset or some other kind of headset or a system which can track the optical points of the transducer. Because if we are not using this headset, then the transducer would move too much, and that definitely distorts the data. So in general, it is assumed that if we are using some kind of head stabilization, like this system 20 years before, or some kind of optical tracking, other kind of optical tracking or accelerometers to track the transducer, or a metal or other type of headset, then this can make sure that the ultrasound data is not corrupted. This is the general assumption, but it seems that even if we are using a headset, there can be problems with the ultrasound data. So the problem is that when we are recording the subjects, of course, they are speaking and the jaw is moving. And in this case, sometimes the headset moves away from the original position. And if we record, I don't know, 200 sentences, it might happen that after a while, the recordings from a later part will be in a slightly different orientation in terms of the ultrasound images. So there is some kind of misalignment in the recording session. And the question is whether we can measure it in some way or how to figure it out. So we had a very simple idea for this to measure the transducer misalignment. First of all, we have, so we are recording the ultrasound data sentence by sentence. And what we did is that for each sentence, we calculated the mean ultrasound image. So we had 200 sentences, and for each of them, we calculated the mean ultrasound image. And we assumed that if we are talking like if there are regular sentences, then this average ultrasound image should show some kind of the neutral or the average tongue position. So this should be the same across the time as we go from the first sentence to the last sentence. And if we compare these images with each other and we calculate like a DTV matrix or a mean square error measure, we can create some kind of error map, which is showing the ultrasound transducer positioning, or whether the tongue is at the same position or not. And there is a resulting matrix from one of the speakers. What you can see here, so the bluish colors show that there is low error, the yellowish or greenish color shows that there is some larger error. So the, the horizontal and the vertical axis are the time, so the number of the sentence, they were recorded after each other. And what we can see that in this first block, so like from sentence 1 to 120 roughly, this is okay. So the ultrasound data was recorded in the same position. But at this point, maybe the speaker did some adjustment of the headset, the transducer moved a little bit away. And after that, this next part is like in a slightly different position on the ultrasound images. And this can cause a problem for the machine learning, because the deep neural network is sensitive for the position of the tongue within the ultrasound data. If we check the data for another speaker, now we don't see as a strong effect. And we did not quantify or compare this with any kind of regression, but it seems that if there is some misalignment in the ultrasound data, then the results of the articulation to speech synthesis will be weaker. So as a summary, in this presentation, we extended text-to-speech synthesis with articulatory input. And we have shown that there is a slight improvement if we add the articulatory data. Again, we were using speaker-dependent network, and some kind of speaker adaptation will be useful later. If you are coming for the interspeech conference next week, then you can find a follow-up paper there. So thank you very much for your attention.
Are there any questions here in the room? If so, please come forward or grab a mic. Anybody? No? Let's see, was there anything in the QA? No. Oh, that's just Javier. It's asking something. Anything else? Anybody have anything? I was wondering something. You were just showing the that overview of how the position could slightly change. Would there be some kind of correction that you might be able to do to that to try to improve the training?
Mm-hmm. Yes, thank you very much for the question. I was just showing like a way of figuring out this error in the transducer position. And the plan is, yes, of course, we would like to fix this some way, but until now, we haven't done any development on this, but that's a future plan. Thank you.
Thank you. All right. Now we continue on to our next speaker, and that will be Javier Latorre from Apple. And I am not sure how that works with remote speakers. So if somebody can help me figure out how to get him up, or do I need to do anything? No? Okay. Thank you.
I guess that is hello. One second. Oh, I think I will need to reconnect.
Dear participants, we need an extra 2 minutes just to connect Javi again and see whether he can share the screen.
Yeah, that seems that this time is okay, right?
It's working, yes.
Okay, perfect. So let me start. Right, so yeah, so the title of the paper, as you can see on the screen, is Combining Speakers of Multiple Languages to Improve Quality of Neural Voices. This work has been done part by me and of course with the help of my colleagues, especially Charlotte Payel, Julie Morrill, and then Yanis Stilianou and Alistair Conkey. So the main motivation is an extremely practical one. We need to deploy every year an increasing number of voices for an increasing number of languages. And usually, in order to achieve good quality or the kind of quality that we want, we need to have in the order of 20 hours of recordings. And we know that this is not scalable. It's extremely expensive. Now, there has been a lot of work reporting mixing of speakers so that we can compensate the lack of data from one speaker with the data from other speakers. But most of this work has been done in single language. So only English, only Japanese, only Chinese speakers. So what we wanted to know is whether we could also use data from other speakers, because of course, when we want to deploy a new voice in a new language, we rarely are going to have the luxury of a pool of 10 or even 6 speakers in that new language. And recording 6 additional voices for that new language can be as expensive or even more expensive than recording a single speaker. So that's the main motivation. It's a purely economical one, if you can say it. But then the second question that we wanted to check with this is that provided that we are training, so since we are going to train on a multilingual environment, the voices that we create in that way will still be polyglots, will they still be able to speak more than one language? So to try to answer those 2 questions, we designed a pretty large experiment. So we consider 8 different languages out of 15 locales. So a locale is a language in a specific place. And because for some of the languages, we have more than one dialect, that's why we have more locales than language. And then for each of these 15 locales, 2 speakers, so 30 speakers in total. Then for each one of the speakers, we selected 1,500 utterances. The reason for selecting utterances instead of data is because it was much easier to pick that. But on average, it's something like 7.5 hours of speech for a speaker, which corresponds more or less to 37% of the data that we usually employ for each speaker. And nothing special about the data preparation on the acoustic side. And on the transcription side, we normalize everything to example, and we did some small tricks like splitting diphthongs or affricate and stuff like that, so that the symbols that we have could be more shared across languages, and we could have some certainty that the same symbol corresponds roughly to the same acoustic realization. So based on that data, we tried 3 different architectures, all based on Tacotron 2. The first one is the standard Tacotron 2, so nothing really to mention about that. On top of that, we tried the suggestion that was from Google's paper 2 years ago of adding a residual variational autoencoder with a very small dimension. They applied that for multilingual training. And we also added a standard speaker embedding and language ID. So blue plus green, and altogether are the 3 architectures that we consider. For the speaker embedding, we use the vector of the inference speaker verification model. And because these D vectors are computed on an utterance by utterance basis, they can still contain some information about the acoustic. So to remove that information, we computed a single Gaussian, multidimensional Gaussian out of that. And at training time, we took samples from that Gaussian instead of using the real embeddings of them for each utterance. For the language, we used a simple one hot, And as you can see, we concatenated that to the input of the attention, and the speaker embedding was concatenated to the input of the prenet and the input of the decoder. Again, this is not something that we proposed, that was from a paper in 2018. So, right, so once we have the architecture, of course, we have two ways of training that. The standard way is a simple step training. So that's what we apply with a single speaker model. And that's also what we can apply with the models that contain speaker information. But if we don't have a speaker information and we just do that, the output voice will sound like a mixture of all the voices. So in that case, we apply fine-tuning. For this, we train the base model for 2.5 million steps. And then we finally fine-tune that only on the data that corresponds to each one of the speakers, each one of these 30 speakers, for another 500,000 steps. We also apply this fine-tuning approach to the model that contains speaker embedding so that we could get an idea about how quality improvement or degradation we could gain from that. So for the evaluation, we run it in the crowdsourced noise evaluation in two scenarios. The first one is what we call in lingual synthesis, in which the text, the language of the text that we want to synthesize corresponds to the language of the voice. And the other one is when they are different. We didn't try any code switching in this experiment. So for the lingual, the first bit where the language match, we run it over all the 15 locales, and for each locale, we put the 2 speakers jointly. So in total, we had the 150 utterances for each one of the 5 models. So it's the single speaker, the 3 fine-tune, and the one with the speaker embedded non-fine-tune. And we also added as an upper anchor 50 recordings and as lower anchor unit selection. So in total, we had quite a lot of stimuli for each speaker. This graph presents the aggregated over all the voices, all locales, and the models. So the yellow bar indicates the median. As you can see on average, and I don't like that but it seems that all the fine-tuned models perform clearly better than both the non-fine-tuned or the single speaker model. So something like 0.1 MOS above. But this graph gives only a rough information about how good that is. So we also computed this table, which is maybe a little bit more interesting. This table provides the significance between each one of the models and the single speaker model, which at the end of the day is the one that we want to compare with. So this is over the 30 voices, how many of them were significantly better, equal, or worse. And here, as you can see, even though for the non-fine-tuned model, even though it looked pretty much equivalent to the single speaker model, there are many more voices for which it was significantly worse than better. All the 3 fine-tuned models, even though they are roughly the same, it seems that when models that are a little bit more capacity, especially the residual variation of the encoder and speaker or speaker embedding are a little bit better, better for 3 more voices than the voice that is just the standard tachotron. So again, nothing really too surprising, except that we were maybe expecting that the voice that contained the speaker embedding as well as the language embedding do a little bit better, but that doesn't seem to be really the case. Something that we also ran, that was the work of Charlotte Bayel, really, and was extremely helpful, was an analysis of the comments of the subjects. Because the numbers only indicate how good or bad a model is with respect to the others, but we don't know why. The 2 main complaints of people for the multi-speaker, multi-language model was pace and pauses. So all the multi-speaker models, regardless of whether it was with or without fine-tuning, are much faster. And I think that that's probably similar to one of the results of one of the speakers today morning, that they noticed that they were faster. We still haven't identified exactly what it is, but I think that it's a combination of speakers speaking at different pace, mixed with the different lengths of the utterances in the batch, and tachotron not being very well at figuring out when it should finish and how to match all the input phonics into the expected duration. We also had many more pause errors in the multilingual model than in the single speaker model. Here, the hypothesis is that the phonetic information alone, the phonetic input, is not enough to disambiguate between content and function words, which is one of the main cues for deciding whether to put a pause or not. And also the punctuation tend to have different values depending on the language. So in some language, punctuation is usually only to indicate a pause. In some other languages, it's needed as a grammatical feature. And the model is not so expert as to make these distinctions. There are also some misplaced word stresses, especially for languages with secondary stress in compound words like German. And sometimes we had a non-phonemic distinctions that were less accurate, like in Italian, the trill and the flap sometimes was confused. That was probably because we didn't have the distinction in the transcription. Now for the second bit, that was the kind of secondary goal. Well, if it was good, it was great, but not in cross-lingual evaluation. We only evaluate that for 4 different target languages in 4 different locales. So for English, we evaluate it in the United States, for Spanish in Mexico, French in France, and German in Germany. So we didn't evaluate it for the other 4 languages. In this case, we evaluated 50 utterances only for each one of the non-native voices, different utterances. And we separated the voices into sets, high pitch and low pitch, because otherwise there were too many voices and the experiment wasn't really going to work. Here, as upper anchor, we only use the native single speaker model, not the real recordings, and the corresponding to the sets of high or low pitch. Here we got a little bit of, in a sense, a surprise. We were expecting that the non-fine-tuned model would perform significantly much better than the others, because we know that when we fine-tune, the model tends to forget what has before. And indeed, on average, it performed better, but not significantly much better. We also found that the combination of what is the target voice and the target language is the most important criteria for the quality, also not too surprising. And from the comments that we got, the main complaint was the foreign accent that was too strong because it decreased intelligibility in some cases. The models tend to reproduce some of the stereotypical features of foreign speakers sometimes, so phonemic distinctions that are lost, or sometimes a phoneme is eliminated, like in the case of diphthongs. So it only the first or the second bit of the diphthong was used sometimes. Or sometimes even a new phoneme was introduced. So one of the French voices, for example, in a Spanish sentence, de animales, introduced a liaison and pronounced it as des animales, introducing an S in the middle. As I said, as expected, the models without fine-tuning are less accented. And something that was more interesting maybe is that the foreign accent is not, the acceptance of foreign accent is extremely locale dependent. So if I can go back, you can see that on average, the most scores for the US are much higher than what we get for Mexico. And Mexican is somehow in between what we have for, and French and German are somehow in between. We tried to run an analysis of that. You can find it in the paper based on the phonetic similarity between the target voice and the target language. But I think that is also more something that is cultural or local dependent. So maybe people in the United States are more used to foreign accents than people in Mexico. Finally, we also had some small degradation or blabber for some of the voices in cross-lingual synthesis that was almost not existing in the lingual synthesis. So I will play a demo. I will only play the British English unless there is some requirement. So that will be with a single speaker. I play in order. So for this, we had the fine-tuned models. Sorry, the multi-speaker model used 56% of the data used in the single speaker.
Javier, you need to also share your audio with everyone.
How do I do this?
Stop the screen sharing, and then when you share your screen, you can, on the left side, you can check share audio as well. So stop screen sharing and share it again, and then you can do it.
Okay. And optimize for video clip.
Yes.
Right. Okay. Let's see if that works now.
In 1818, Mary Wollstonecraft.
Can you hear now?
Yep, we can hear you.
Sorry.
In 1818, Mary Wollstonecraft Shelley took the next major step in the evolution of science fiction when she published Frankenstein, or The Modern Prometheus. In 1818, Mary Wollstonecraft Shelley took the next major step in the evolution of science fiction when she published Frankenstein, or The Modern Prometheus.
So the quality is better, but it has this post error before Shelley. The next two do not have that mistake.
In 1818, Mary Wollstonecraft Shelley took the next major step in the evolution of science fiction when she published Frankenstein, or The Modern Prometheus. In 1818, Mary Wollstonecraft Shelley took the next major step in the evolution of science fiction when she published Frankenstein, or The Modern Prometheus. In 1818, Mary Wollstonecraft Shelley took the next major step in the evolution of science fiction when she published Frankenstein, or The Modern Prometheus.
And the non-fine-tuned model is faster and flatter in terms of prosody, which is also kind of expected. So finally, for the cross-lingual, I will play one sample of what is the singular speaker.
The upside-down face emoji can convey sarcasm, passive aggression, or irony.
And then for German, all the models.
The upside-down face emoji can convey sarcasm, passive aggression, or irony. The upside-down face emoji can convey sarcasm, passive aggression, or irony. The upside-down face emoji can convey sarcasm, passive aggression, or irony. The upside-down face emoji can convey sarcasm, passive aggression, or irony.
So as you see, all the models are accented. The last one is a little bit less accented, and maybe the 10 is.
The upside-down face emoji can convey sarcasm, passive aggression, or irony. The upside-down face emoji can convey sarcasm, passive aggression, or irony.
So, yeah, to conclude it, so we have shown in a large experiment that indeed lack of data from one target speaker can be compensated with data from other speakers, even if they are in different languages, that compensation is equivalent to more than doubling the amount of data that we have for a singular speaker, and that to some extent the models trained in this way also preserve some level of multilinguality or polyglot, even after fine-tuning. And finally, that the main problems, apart from the foreign accent, are based on post-prediction. Yeah. Now, that's really it. I guess that
come up here.
Hi, first of all, thanks for the inspiring paper and presentation. I'm very interested because I myself work with TTS for under-resourced languages. So apologies in advance for having many questions. My first question is about the amount of data that you use. If I'm not mistaken, you use around a total of 200 hours in total for all languages and locales, and around 15 hours for each locale or language. That is, in my opinion, not exactly little. So my question is, did you also consider experimenting with even fewer data, let's say 5 hours for each locale or language? And sorry for having many questions. And the next one is also related. You based your architecture on Cyclotron 2, and it is also mentioned in the paper that you train on only one GPU and with a batch size of 16. I would imagine that took a lot of time to train. My question is, did you also consider maybe other architecture that was maybe less demanding in terms of computing resources? And the last question is about the balance in the data for each locale in the combined training data. So right now, you are using the same amount of data for each locale in the combined training, the whole data set. Did you also consider using, let's say, more data from languages that have that share more in the phonetic space with the target language? So in other words, the phonetic distance that you also use in your paper would be closer between those languages in the training data and the target language. Maybe that would also increase the performance in lingual synthesis itself. That's all from me. Thank you.
Thank you very much for 3 excellent questions. Actually, we are investigating all 3 of them in a sense. So we are running an experiment now with gradually decreasing the amount of data that we use for every new locale for a given language, see how that operates. We still don't get the results, but that's of course one of the things. And I agree that 8 hours of data for a new voice is not little. It's just in the context of what we tend to use, it's still a significant improvement. And as I said, this is more toward more commercial applications. About the training with other architectures, yeah, we run some experiments as well on distributed training with multiple GPUs. It works as well, but in general, the quality that we obtained was a little bit worse than with a single GPU, which is the reason why in this paper and this experiment, we stick with a single GPU. But there are other architectures, the parallel ones, for which the training time is significantly reduced. So for these 3 million steps, it took roughly 3 weeks. And with other architectures, you can probably reduce it to 3 or even 5 days. And regarding the balance of data, that's another set of experiments that we are running on now. The question there is whether it's more important to have speakers that share the phonetic similarity or to have speakers that are closer in the speaker space. So we're still running this kind of things and trying to find what will be better. Hopefully we can have a paper soon and I can share the results with you.
Okay, very nice. I think there was a few questions in the chat. Thomas Strogman says, how do you explain the faster speech rate in multi-speaker modeling?
That's the $1 million question. So we have the hypothesis that we are working with is that every speaker that we have has a slightly different speaking pace. And when we put all of them together, especially because we choose the sentence for training, the utterance for training randomly every batch. So some of them require a lot of padding, some of them require less padding. And for whatever reason, sometimes we found that the longer the sentence, the faster the pace, which seems to indicate that Tacotron kind of figure out what should be the average length of an utterance and then the attention mechanism try to fit as many phones as possible in that. But as I said, that's still on the hypothesis level. We have switched to different type of models and we have kind of stopped that investigation.
Thanks,
I see.
Owe you $1 million now. Thanks.
I think there is a question by Simon. It seems that multi-speaker models have worse prosody than the single speaker ones. You're using examples and explicit common representation for phonetic information. In contrast, prosody is only modeled implicitly. Does this suggest that we need an explicit representation of prosody to allow multilingual modeling? Probably yes, the question is what? So we include the stress marks on but that seems to be not enough.
Gérard has a question.
Yeah.
Yeah.
Hello, Gábor, it's Csapó here. In fact, I have a similar question to Simon. In fact,
sorry, Gérard, I cannot understand you. If you could come forward, please. Sorry. It's all the echo on the room.
So, as far I understand, in fact, you don't have word boundaries. You don't have word boundaries. You don't have any punctuation marks. So, in fact, you are synthesizing some script somehow. Modern languages have spaces between words. Could you explain this very carefully?
Yeah. So the input is the standard way on. I thought that it was a standard. That's why I didn't explain. So the words are converted into phonemes, and then we include the word boundaries and punctuation marks. That's all. And for the phonemes in the accented syllable, the stressed syllables, we have different symbols for the stressed and non-stressed syllables. Sorry, vowels.
Access to syntactic information, somehow to prosody, because if you have just a flat phonetic form, of course you don't have any means to predict prosody. But it's not your case.
No, we have word boundaries and punctuation and stress marks, but we don't have syllable boundaries or anything else. That's why I said I don't know what kind of additional prosodic feature we could extract in a shallow way from the text, other than.
Problem of pause is not coming from, the absence of stress or whatever.
Yeah. The problem with the pauses is that when you have only the phonetic transcription, even if you have the word boundaries, the word which is content in one language can become function in a different language. So in a single language, that kind of works, but when you have multiple language mix, that doesn't. So the model cannot identify that after this phonetic sequence, I do need to pause.
Of text reading or text writing, where you have an author which using a lot of punctuation versus an author so you can have a miss. Okay, thanks.
Yeah, so Simon says punctuation is an explicit representation of prosody in some sense, but it's very limited, obviously, and it's not used in a consistent way across languages. I had a final question, if that's okay, before we move on. Do you think that you say you're using Xampa and try to unify it across languages? Do you think that's part of your problem with some of these languages, the accents still coming through? Because you could have, say, a flap T versus an aspirated T, or a rolling R versus an English R, but you're using the same phoneme symbols for those?
Could be, but then you would expect that once we add the language embedding, that should be enough to disambiguate between them, and that doesn't seem to be the case. Okay. So it could be, I don't say not, but the other risk is if we have every phoneme for every language completely independent, that when I put the phonetic sequence from one language, what do I get? Whatever I do is the voice of the speaker in that language. Because there seems to be, in the decoder, there seems to be always a kind of conflict between the information that comes from the decoder, so the embeddings from the decoder, and the speaker embedding. So depending on the training stage or the architecture, sometimes everything pivots toward the speaker or pivots toward the phonetic sequence. So
thank you. Okay, I believe the next speaker is Christina Tonander, if I say that correctly, from KTH.
Yes, hello. I'm sharing my presentation.
Christina, we don't see it yet.
It takes some time. I think
it's coming. Okay, that's right. The method.
Right. You can see it. Yeah. Okay. So, hi. I'm Kristina Tanander. My co-author is Jens Edlund. We're from KTH, Stockholm, Sweden. I'm also affiliated with the Swedish Agency for Accessible Media. This is an agency with a mission to provide people who can't read printed text for one reason or another with adapted text, such as talking books or audiobooks and Braille. And we do a lot of university textbooks and use with speech synthesis. This study is part of a project, deep learning-based speech synthesis for reading aloud of lengthy and information-rich text in Swedish. Thank you, Vinnova, and thank you, Swedish Research Council. The goal with the study is to evaluate methods to slow down existing speech synthesis. And we do that by manipulating the input to the synthesis, by inserting pauses at certain locations, or by manipulating the output. And this means that we are making the pauses longer, or we are stretching the speech signal of the synthesized speech. Our scope is that language learners and people with cognitive impairments, such as dementia or aphasia or something else, often require a slower speaking rate to be able to understand the message, and they need a longer processing time, especially when listening to longer texts read aloud. And as I said, we assume here that we don't have access to slow readings for training a slow speech, a slow TTS system, but we use existing voices and manipulate the input or the output of them. Something about speaking rate. Here we define it as the rate at which a certain idealized unit is produced per total speech and non-speech duration. And articulation rate, on the other hand, is the same units, but per actual speech duration without the non-speech segments. The units used can be phonological or phonetic, such as syllables or nuclei, phonemes or phones. It can be orthographic units, such as words. The time units are typically seconds or minutes, but there are also metrics such as average syllable durations and so on. And here with non-speech segments, we mean silences or pauses or breaths. And these are the definitions we use, but it's always wise to check when reading a paper about speech rate or speaking rate, if the non-speech segments are included or not, how the units are defined, if it's the intended or the realized units there that is counted. And just for our reference, some typical speaking rates in English, if we look at syllables per minute, about 200, 250, or 3 to 4 syllables per second, and 150 to 200 words per minute, 2 to 3 words per second. Slow speech is typically characterized by a larger number of pauses, and the pause durations are longer, and so are the phone durations. F0 is typically lower, and the speech is hyper-articulated and contain more syllables than speech at a normal speaking rate or fast speech, because there are less reductions. Speaking rate can be influenced by regional variation, so that people in one region speak faster or slower than in another region. Also the number of syllables in the utterance, the longer the utterance is, the faster it goes. And also the purpose of the message. If it's a TTS recording, it's typically quite slow. Spontaneous speech is faster than read speech, and so on. And the manipulations we were talking about here was stretching the speech signal, while of course maintaining F0, inserting more pauses and making the pauses longer. We should also mention that controlling prosody is, as you know, a highly active research area today, and modern TTS systems are really good at capturing prosodic features. And speaking rate and other prosodic phenomena can be controlled at different levels with success, even at phone level. The listening tests which we performed to listen to different stimuli consisted of 2 parts. We had 64 participants in each, and they were recruited through Prolific. They were paid 80 pence per test, and each test took about 5 to 6 minutes to perform. The listening test platform was developed by Språkbanken Tal, an infrastructure for Swedish speech technology, and is WCAG compliant, which means that also blind people can use it if they use, for example, screen readers. Our evaluation question was framed like follows. Imagine that you have requested a short text to be read for you very slowly. How well does this reading match your expectations? And then we had a scale from very well to very poorly. The voices used. We had the human voice, a Swedish female professional speaker. And then we have the synthetic voice. It was a tachytron voice built from data of the very same human female speaker. So it was the same voice, both in a human and synthetic representations. The TTS, it's possible to synthesize speech at 5 different speaking rates, but as you say, it's trained on speech at normal speaking rates. So the differences between the 5 categories are not huge. You can say that the slowest speaking rate is hyper-articulated and a bit slow. Okay, so we used 2 Swedish texts from a campaign concerning COVID-19 information. And they were both recorded with a human voice at the normal speaking rate and at a slow speaking rate. And the recording with a slow speaking rate we use as a reference utterances. And as I said, we synthesized the synthetic data at the slow speaking rate. But as you can see, the human slow reading was about 30 seconds. The TTS slow reading was 19 seconds, and the human reading at the normal speaker rate was 17 seconds. So the slow TTS was more close to the human normal reading. Each of the 2 texts contained 2 sentences, about 30 words and 60 syllables. So I'll try to guide you through this slide. In the upper table, you can see our 8 stimuli. The first one with a black background, A, ref, is the reference human slow reading. And the duration of these reference stimuli were about 30 seconds, and all the other stimuli were then matched to reach this duration of 30 seconds. And this was done, as I said, by inserting pauses and or stretching the speech signal or prolonging the pauses. So if you look at the pause placement column, you have human slow, hum slow. These are the human pauses in the slow reading, and they were also used in 2 of the synthetic stimuli, G and H, the blue and green one at the bottom of the table. Then we have B, human stretched. This is the human normal reading. And as you see in the number of pauses column, it contains 6 pauses, and in text 1, and the human slow reading contains 16 pauses. So there's a quite big difference there. Then you have orthographic pause placement, where we inserted pauses at minor and major delimiters, commas and full stops. Designed pause placement, roughly at major phrase boundaries. Word pauses, we inserted pauses between each word, and then you have the human slow locations again. Then you have the prolongation column. the human normal recording and one TTS recording, they were stretched to reach 30 seconds. And then you have in D to G, you have inserted pauses that were prolongated. And in the last stimulus, the pauses were first prolongated and then the whole utterance was stretched. And I should also say that in D to G, the durations of the pauses were altered to match the duration proportions of the reference files. You can see a visualization of the pause distribution in text 1 in the lower part of the slide, where the black bars are represent speech and the gray bars non-speech. You see to the left, the black arrow, this is a reference utterances in text 1. And it's there twice because to make it clear that, to make it easier to see at the very bottom, the comparison between the 3 stimuli using the human slow pause locations. In the non-speech column, you see the proportions between speech and non-speech. The reference utterance in text 1 contained 20% non-speech. The human recording and with a normal speaking rate, half of it. TTS design pauses, the double, and H, TTS human pauses stretch is the one that got closest to the reference reading. And finally, the last column shows the average pause durations, 330 milliseconds in the reference stimuli for text 1. And you can see that, again, the green one is the one that matches the reference reading the best. And then you have the TTS orthographic pauses, where pauses were inserted at just a couple or 3 or 4 locations. Those pauses got really long, about 5 seconds. And this is 15 times the average pause duration of the references. Some results. There was no significant difference between text 1 and text 2. And this means that we could combine the 2 texts in a further analysis. And it showed that there were significant differences between stimulus types, the different types of manipulations. I could also mention that there were significant differences between the reference stimulus and all other stimuli. So we see that our reference utterance got the highest score. If we allow ourselves to convert the very well to very poorly scale to numbers, it got the score of 4.2. And we can listen to this utterance.
Till exempel kan man med hjälp av lagen stänga köpcentrum och gym.
And on the first place of the manipulated stimuli, we have the TTS human pauses stretch, which was the one with the most similar proportions to the reference utterances, with a score of 3.4.
Till exempel kan man med hjälp av lagen stänga köpcentrum och gym.
Next, on second place was TTS word pauses, with pauses inserted between each word. This was a surprise for us. We didn't think it would score that high, but almost very close to the first place with a score of 3.3.
Till exempel kan man med hjälp av lagen stänga köpcentrum och gym.
And not surprisingly, and our last example here, the worst speech sample with a very long pauses with an average pause duration of 5 seconds with a score of 2.4. And we don't need to listen to this one. It's just a lot of silence. So conclusions, what have we done here? We have seen that the method met our expectations. We saw that the bizarrely long pauses gave significantly worse result, and the speech sample close to match the human slow reading was significantly better. And we have seen that there are variable means of significant and full automatic slowdown of existing TTS, and this is by inserting pauses between each word. And the subject listened to 30 seconds of speech, and even if this is longer speech sample than usually used for TTS evaluation, it's not long enough to tell what actually happens with comprehension and listening fatigue if you would listen to for a longer time for a book chapter or so. And in the future, we will perhaps make a more structured study where we pay more attention to the proportions about speech and non-speech, using longer speech samples and perhaps also fully automatic manipulations. Okay, thank you. That's all from us.
Thank you, Christina. Any questions? Anybody? Géza?
So if I understood you correctly, so it was the slowdown was only slowing down by pauses, so no influence on the articulation rate.
Yes, it was also, it was different. It was either pause prolongation or the speech was also stretched in a couple of cases.
I guess it's, at least we had with some earlier similar studies, and for example, for speech therapists, it was an interesting experience when they said we kept the prosody as it was before, but both the articulation rate was smaller and also the pauses were longer, but the prosody was like standard. So it was not like each word is a separate, as if it was a separate pronunciation. So for you can speak like this, and to understand that, that's very boring. So it's a question whether are you planning to implement something like that?
Sorry, did you mean to implement? I'm not sure I understood your question. Can you take it once again, please?
So I mean that, for example, for a statement, you always have a falling pitch, of course, with the word accent put on that. So in this implementation, did you have this like standard prosody? Because I don't speak Swedish, so I was not sure whether it was like pronouncing one word at a time and then varying the pause between them, or you kept the normal like falling intonation, and you just inserted in between the pauses.
No, it was synthesized. The one with the pauses between each word, it was synthesized one with like commas between each word to make the pauses, and then we manipulate the duration of the pauses to be relatively long, proportionally long according to the so it was longer pauses at the commas and full stops and so on, but the pauses between the words were the same length approximately.
Okay, I had a quick question. You said you had a tachytron model and you had the human speech both in slow and in normal speaking rate. First off, how much data did you have to train this tachytron model, and did you have separate embeddings for the slow versus the normal speaking rate?
Oh, it was done, okay, it was 17 or 18 hours of data, Swedish data, from the same speaker. And these were recordings originally done for unit selection synthesis like 10 years ago or something. So that was our training data. But what we did was that we didn't have different embeddings. We just inserted numbers before each word. We first measured each word in the training data, the approximate syllable duration or articulation rate. And then we inserted numbers before each word, 1 to 5, where 1 was the fastest and 5 was the slowest. And then we can just use those numbers when synthesizing by inserting those numbers before each word in the input to the TTS.
Okay. Yeah, I just wondered how. I just was wondering. Your tachytron slow mode was more like the normal speaking rate.
Yeah, because I mean, the slowest fifth of the training data was not that slow because, I mean, it was mostly consisted of shorter utterances and so on. So it's more like hyperarticulated than slow. Yeah.
One question in the chat. How was the stretching of words performed? Manually?
It was done, we used Audacity, the functions in Audacity to stretch it.
That's just a uniform stretch across the whole word.
Yeah, and it kind of destroys the speech signal as well. It destroys the sound. So yeah, we asked the subjects to not pay attention to that, but you never know what they actually listen to. So.
Okay. All right. Thank you.
Thank you.
Okay. The next speaker is Joachim Gustafsson from KTH.
Yes. Hello. So do you see the screen?
Yes, we can see. Perfect.
And can you hear this?
How are you?
Yes, we can hear
you.
Great. Then I can start. So this is a paper where we are investigating to what extent the speaking style and addition of fillers influence the perception of personality in synthetic speech. And more specifically, we are interested in spontaneous speech synthesis. So this is, for us, something which we have found being useful for both if you want to build like conversational systems like chatbots or social robots. But also we have several projects where we are aiming to make use of the spontaneous speech synthesizers that we have built on found data and see if we can actually investigate the combined perceptual impact of features such as speaking style, the prosodic realization, and the insertion of breathing, fillers, and discourse markers. So just to recap for everybody, the personality traits that we are using here is this big 5, where we have looked at all these apart from agreeableness, so extroversion, openness, neuroticism, and conscientiousness. And for us, filled pauses are very important because in human-human communication, filled pauses have been found useful for the listener because they are used as a turn handling cue. They can improve comprehension of upcoming important information. And also they can be used to get the feeling of how uncertain the speaker is about what they are saying. But they have also been found, if you use them more or less, to also influence the perception of these personality traits. So they could lead to things like neuroticism and preparedness, that you are unsophisticated or insecure. You use a lot of filled pauses in your speech. Discourse markers have also been found useful in human communication. So discourse markers like and I think are used to get some kind of confirmation of understanding from the listener. Those things like I mean and like can be used as hedging devices, or to mark that you modify the content of what you just said to make it not as strong. And also if you use a lot of likes, it could be markers of things like conscientiousness, casualness, solidarity, spontaneity. It's also, of course, known that young people might use them more than old, so they also tell something about the age of the speaker. And also, of course, prosody influence the perception of personality. So extroversion have been associated with fast speaking rate and a wide pitch range, but introversion is more soft and slow and deep and monotone. Faster speech rate have been found to have some kind of influence on the perception of social attractiveness, persuasiveness, and dominance. And this is actually, we are doing a restudy. So that there is a study by Miriam Wester and others that in Interspeech 2015 did a study on adding fillers and to an existing unit selection synthesizer. And they found that if you add fillers, it makes it more neurotic, less open, extrovert, and conscientiousness. And in a follow-up, they also found that if you increase the voice quality, it can enhance the personality that the text convey, but it doesn't alter it into another personality. So of course, it's not only the way you speak, but also what you say that influence the perceived personality traits. So what we have done here is that we reuse their text material that they have designed for their study, and also their read speech samples that they have made available open source. And one thing about these text materials is that they are meant to designed to elicit these personality traits. So they're not neutral in that sense. So what you can do if you add these things like you know and like is that you can enhance certain personality traits in the perception. So like I said, we use the original read speech, which is a Sarah voice, a female Scottish voice talent of read speech, one of their better voices. It's of course read speech, but what they did was that they took in the original voice actor voice talent and had her read these fillers and these you know I like and so on, and then inserted them into the synthesized speech. What we have developed is a system where we make use of conversational or spontaneous monologues or dialogues, where we first detect breaths automatically and then use breath groups as the unit that we synthesize. So what we have is that we have an Irish corpus of an actor that was talking about anything for like 10 minutes in 25 different sessions. So just talking. Then, of course, that one includes spontaneous fillers because it's hard to just talk for 10 minutes about nothing. So what we have done is that we use our Articulatory where we first train it on LJ speech, and then we fine tune it to this 5 hours of monologue, spontaneous speech. And then we have also fine tuned the waveload to get the voice better. And for Swedish, we have the same, but there we used a male Swedish actor voice talent, where we have like 10 hours of read speech with no fillers because it's recorded for unit selection. And then we have a podcast where a Swedish comedian talks with another guy for like 6 hours, where we of course also have spontaneous fillers. And in the study, we are using the same personality questions as used in the previous study. So the way they answer questions are: do you think this person would start a conversation? Then you increase the extroversion and so on. So in the first experiment, we took both Swedish and English, both fluent and non-fluent. and read and spontaneous. And for each language, we recruited 60 participants for their prolific, and then we have the statements of the question statements, and then they had to say how much they think it would be likely or very unlikely that it would match that speech file. And we used 30 subjects per. So overall, we can say that we got the same results for English read speech as in the original study. So more neurotic and less of the others. It's the same tendency, the same direction for English spontaneous speech, but less so. So only extroversion and openness are real here. I mean, are significant. And just to get an idea of how it sounds.
You don't seem to have made much effort. Though given the losers here, I'm not surprised. You'd probably be happier, watching TV at home.
Then
I'm great at helping others plan and cooperate to get things done. It's important to work out what can be done and the best way to do it. I mean, I like to work with others and help everyone come together behind a project.
You don't seem to have made much effort. Though given the losers here, I'm not surprised. You'd probably be happier,
I'm good at encouraging others to contribute effectively. I think it's important to enjoy your work and to be enthusiastic about what you do. If you can make work enjoyable, then the people around you will also become more.
I like to plan, provide direction, and make sure everyone knows what their responsibilities are.
You don't seem to have made much effort. Though given the losers here,
For Swedish, it's slightly different. Here we actually have no difference between fluent and disfluent examples. And also, but what we have is that there's a difference between spontaneous and read speech voices. So yes, show you some examples here.
Du verkar inte ha gjort stora ansträngningar. Men med tanke på förlorarna här är jag inte förvånad. Du skulle förmodligen vara lyckligare om du var hemma och kollade på TV.
Ja, jag är bra på att hjälpa andra att planera och samarbeta för att få saker gjorda. Det är viktigt att ta reda på vad som kan göras och det bästa sättet att göra det. Jag menar, jag gillar att arbeta med andra och hjälpa alla att känna sig delaktiga i ett projekt.
Vilken röra det är på det här stället.
Okay, and then we went on to the next study where we wanted to see, because in the Swedish version, we actually trained it using a multi-speaker tachotron where we could actually mix between the two voices using a speaker identity vector. So what we did that we had it either only read speech and then 90%, 50%, 10% and 0% read speech and just were able to generate the same prompts but with different amounts of mix, and we tested that also in prolific. And what we found there was that the biggest difference in this is in extroversions. I will play those some examples here you can hear. So first it will be 100% spontaneous and then less and less spontaneous.
Du verkar inte ha gjort stora ansträngningar. Men med tanke på förlorarna här är jag inte förvånad. Du verkar inte ha gjort stora ansträngningar. Men med tanke på förlorarna här är jag förvånad. Du verkar inte ha gjort stora ansträngningar. Men med tanke på förlorarna här är jag inte förvånad. Du verkar inte ha gjort stora ansträngningar. Men med tanke på förlorarna här är jag inte förvånad. Du verkar inte ha gjort stora ansträngningar. Men med tanke på förlorarna här är jag inte förvånad.
So what we can conclude here is that we got the same results as in the original study, which is good because it's the same samples. But when we add it in the spontaneous speech, it's less of an effect. We only get it on extroversion and openness significantly. What we do find is that the spontaneous speech with fillers are significantly more open and less neurotic than red speech versions with fillers. And for both Swedish and English, the spontaneous voices are more extrovert, regardless of fluency. For Swedish, fillers did not change, as I said before, but we did a third study where we looked at perceived spontaneity, and it actually makes it sound more spontaneous. And the spontaneous samples were less open and less conscientious, which is, it should be the opposite, but the thing is that the red voice had slower rate, lower pitch, and a more coarse voice quality. So why do we have a difference between these voices? So one difference is that in this unit selection voice, the surrounding speech and the fillers weren't matching, so then they became more prominent. While in the way we did this, we treated fillers as any words in the TDS, which means that the prosodic realization of fillers and surrounding is cohesive. So if we insert a filler like the speech afterwards before will be actually slower and more hesitant. While if you have, an alike, it might be even faster. So it actually makes it more coherent. Another thing is that it's multidimensional personality. Of course, it depends on, here we had text that actually portrayed different personalities, and the prosodic realization and fluency and voice quality also realizes it. But if we treat them as words, we can actually enforce a more spontaneous speaking style, and we can support but not alter the personality aimed for in the text. And we think it will be interesting to continue looking at co-training red speech voices and spontaneous speech voices so that we can adjust. If we use 10%, we can actually even make a red speech synthesizer do fillers better. And we might be able to make entirely new voices that are in between. Thank you.
Any questions in here? Gérard? Get your steps in.
Oh, yeah.
No, you're fine.
Hello. Just for me to understand precisely what you have done. In fact, the transcription of these fillers are comparable to normal text.
Yeah, we use
normal text. So there is no special tag saying this is a filler.
We are actually using phonetic transcription as input here because we didn't have that much training data. We didn't use orthography, but actually transcription. So then the fillers and breaths have their own. So fillers are or am, and we have a special token for breaths and silent pauses.
The test utterances are you insert, in fact, the fillers as the same place where it has been uttered by the speakers, and in fact, you for going to 10% to 100%, somehow you sample, you say eliminate a given percentage of these fillers, or what are you doing exactly?
No. In this percentage, it's we trained the multi-speaker. So we trained in the same tachotron. We trained on both the red speech corpus and on the spontaneous speech corpus. But we gave the speaker identity as input embedding as this multi-speaker, so that you can tell it how much percentage
for generating 10%. For generating 10%, you in fact eliminate 90% of these fillers.
No, the fillers are the same. It's the red speech corpus didn't have any fillers, but it actually, just by co-training it with a spontaneous speech corpus that has fillers, it actually learned. This is the crazy stuff. So it actually is beneficial if you want to train a red speech voice, even if it's 100, at the end use 100% of that, it will still be better at uttering filled pauses than if it hadn't been co-trained with the spontaneous speech. And then you can...
I think what's unclear for Gérard is when you're synthesizing, don't you have to explicitly put the fillers in your input?
What we do is I just say the position in the text, so to speak, where they should put them. So it's not up to...
No way to say, okay, the 10% version has fewer fillers than the 100% version.
No. That's why we can do in both spontaneous and red speech, we can tell it where to be hesitant or where to add, or I like and stuff like that. So it's a text input where you control that. But we have done previously studies where if you don't tag the fillers, Tachytron will actually add them itself where it actually makes sense from the training material. But then you don't have control over where they are. So here we use the version where we actually manually annotated all the fillers. So we have control.
Okay, any other questions here? I don't see, oh, there's one on the chat. Okay, let me see.
Yeah.
Do you want me to read it or do you want to read it?
So the voices with different amounts of spontaneous red speech, to me it sounded like the voices became more or less like the other speaker. Yeah, I mean that's what happens if you have 10% only. Of course, it will be mostly of that speaker. And the problem is if you put it in the middle here, you will get something which sometimes sounds. I mean, during the same utterance, it could actually change between the two. So it's really not the perfect way to do it if you have such a different voice quality.
So that's the follow-up question. Could you try to keep the speaker identity
fixed? Then we need to do something. Yeah, I think then we need to do something. Yeah, then we need to do something smarter with the training and the network.
Okay. Thank you.
Yep. Thank you. Bye-bye.
Hej då. Okay, and then next, the last in this session is Tamás.
Hello, everyone again. In the last presentation of this session, I will talk about how we applied Hungarian Tachytron-based text-to-speech synthesis for articulatory to acoustic mapping. This work was mainly done by my colleague Csapó, who is the first author, but I will give the presentation. So here, the topic is similar to the first presentation in this session, which is articulatory to acoustic mapping. And we would like to synthesize speech directly from articulatory input, again with ultrasound prompt imaging. The difference is that in the first idea, we were using the so-called direct synthesis approach, which means that directly from articulation, we are converting to vocoder parameters, like spectrum, excitation, and so on, to synthesize speech. So the direct synthesis has the idea that there can be a small delay between articulation and the speech generation, And this might be suitable for real-time application, like with a very small delay. There is also another approach for articulatory to acoustic mapping, which is the recognition and synthesis approach. Here, the idea is that first we are recognizing the textual content from the articulation, and after that we can use a standard TTS to synthesize the speech. The disadvantage is that there might be more error possibilities. For example, there might be misrecognized letters, which if they are there at the input of the TTS, then they can cause some trouble. But on the other hand, the big advantage is that the final audio quality might be much more natural because we have like a regular text-to-speech at the output. So we had some earlier results in this field, like autosound to spectrum, autosound to excitation, and also combining autosound and text in this purpose. The goal of the current study, as I told before, is to combine these earlier results in direct synthesis and especially focus on the recognition followed by synthesis. Also, we wanted to check how we can apply our recent Hungarian Tachotron 2 model to have a higher quality final speech output. So the method that we are doing in this work is the following. There are three main steps. First, from the autosound articulatory input, with a three-dimensional CNN, we are transforming it to textual representation, so symbols. After that, from the symbols, we are transforming with Tachotron 2 to Möller spectrogram. And finally, with the neural vocoder, with Waveflow, we are transforming synthesizing speech from the Möller spectrogram to the final wave. For the articulatory data, we were using Hungarian data that were recorded at the Lingual Articulation Research Group in Budapest here. We have synchronized audio and autosound recording. For this study, we were only using a single female Hungarian speaker who had roughly 450 sentences recorded in 5 different sessions. So like you can see that on the images, the tongue is at different positions because they recorded at different days. For the audio data, we were using previously recorded Hungarian database, which is precisely labeled, segmented, and parallel in a way that all of the 11 speakers have the same textual content. So there are roughly 2,000 sentences for each speaker, which was originally recorded for unit selection speech synthesis. And altogether, it is roughly 22 hours of Hungarian speech data. And we were using this for the Tachotron 2 and Waveflow training. We had a baseline system, which is converting directly from ultrasound to Möller spectrogram without the textual representation. So this is like the approach of the direct mapping. Here we were using three-dimensional CNN which is taking into account both the temporal and the timing information. So several consecutive ultrasound images are used in the 3D CNN. And we are using 80-channel Möller spectrogram representation with the following 3D convolutional network. In the proposed system, which is doing the recognition to text part, in the first step, we are from the ultrasound tongue images, we are converting this to symbols, which are basically the text or phoneme representation of. So these are the Hungarian symbols. Again, for this, we can use the same data. And here we have 93 different symbols, which are representing the Hungarian short and long vowels and consonants. The only change compared to the previous 3D CNN is that now we have softmax output and 93 neurons in the last layer. If we check the confusion matrix of this ultrasound to text, there can be a couple of observations. This big matrix in the paper where it's easier to check, but I will tell you what is the most important part. That so the question was that which of the speech sounds are mostly recognized when we are recognizing it from the ultrasound input, and we had the lowest accuracies with the vowels a and a, and also with the nasals m and m. So these based on the articulation, these can be easily confused. Also, some of the stop consonants which involve like bilabial and information, so like the lips, which is not included in the ultrasound. Of course, that's impossible to recognize just from the ultrasound. So they are also mixed up in the ultrasound to text conversion. So we can see that it's mostly working with 0.68 validation accuracy, but still there are a couple of errors in the recognized text. In the next step, we are using the tachotron tool for the symbol to MEL spectrogram conversion. So this is similar to the original tachotron 2 paper. The difference is that we are training it on Hungarian data. So with 22 kilohertz speech, we trained it for 15600 iterations. And again, 80 channels were used for the MEL spectrogram representation. We wanted to keep the timing of the original ultrasound recordings. So we did it in a way that in the tachotron 2, the symbols are repeated according to how long the specific vowels are in the data. And for this, we were using the full audio database. We had two variants of this proposed system. The first one, the simple, is that we are adapting to the female speaker to these 400 sentences of the audio. The optimal setup was when we had 84 iterations. And for the second version of the proposed system, we had another idea. I mentioned to you that in the ultrasound to text confusion matrix, there were a couple of misrecognition errors. So we had the idea that, okay, we could do it in a way that those speech sounds which are misrecognized, they could be trained in this tachotron 2 system, because tachotron 2 can tolerate if there are errors in the text input. So we did some kind of data augmentation in a way that we created data based on the mistake distribution of the classification matrix, and we further trained this system, but otherwise we were using the same females data. For the neural vocoder, we were using WaveGlow, again with the 11 speakers, 22 hours data set on 8 V100 GPUs for 600,000 iterations. And so the final synthesis is created from 3 components: ultrasound to symbol, symbol to MEL spectrogram, and MEL spectrogram to speech. We synthesized sentences which were, of course, different from the training and validation. The test sentences for synthesis, they are coming from the Hungarian version of the North Wind and Sun. These are 9 sentences. And we conducted an online subjective listening test, like a Mushra-like listening test, when the naturalness had to be changed by the subjects between 0 and 100. So the higher is the better. 23 Hungarian subjects took part in the experiment, which was roughly 10 minutes long. You can see the results of the subjective listening test here. So the different colors show the different system. The first is the original natural sentences. The second is a lower anchor, which was like the distorted version of the original sentences. This gray, it is the direct ultrasound to speech mapping with the 3D CNN. And the two red versions, they are the recognition and synthesis approach, so which is basically the idea of this paper. The first one is when we were just training regularly by the adaptation, and the last column shows when we also took into account the errors of the classification matrix. According to the average results, the red ones, they significantly differ from the baseline system, but the two proposed ones, they are not significantly different from each other, but there is a slight improvement based as a result of this additional data augmentation. I will show a couple of samples which are in Hungarian. First, an original version.
Az északi szél nagy vitában volt a nappal, hogy kettőjük közül melyiknek van több ereje.
This is the baseline direct synthesis.
Az északi szél nagy vitában volt a nappal, hogy kettőjük közül melyiknek van több ereje.
And after that, the recognition and synthesis.
Az északi szél nagy vitában volt a nappal, hogy kettőjük közül melyiknek van több ereje.
And the second one with data augmentation.
Az északi széllam hitam volt nappal, hogy kettő közül melyiknek hat több ereje.
So the main difference between the direct synthesis and the recognition synthesis, as you could hear, is that with the direct synthesis, the overall quality is lower because there are strong vocoding effects. So that's an issue there. In the recognition and synthesis, the individual speech sounds, they are better because they were synthesized by the Tacotron 2 model. But sometimes if there is a problem in the text recognition, then of course there will be a problem in the final output. The next sentence is another way when this is more audible. Again, an original version.
Egyszer csak egy utast pillantottak meg, amint köpenyébe burkolódzva közeledett.
Then the direct mapping.
Egyszer csak egy utast pillantottak meg, amint köpenyébe burkolódzva közeledett.
And after that, the recognition and synthesis.
Egyszer csak egy utast pillantottak meg, amint köpenyébe burkolódzva közeledett. Egyszer csak egy utast pillantottak meg, amint köpenyébe burkolódzva közeledett.
So if you know Hungarian, then it's very difficult to understand what is the content in this sentence because there were a lot of errors in the text representation. So in this research, we were comparing direct synthesis and the recognition synthesis approaches for the ultrasound to speech synthesis. Here we were doing in 3 steps: ultrasound to symbol, symbol to mass spectrogram, and mass spectrogram to speech. And we were applying our previous Hungarian Tacotron 2 model for the final speech output. In the future, of course, we plan to use the Ultrasound repository for English experiments, and also we would like to have a fully end-to-end model. Thank you very much for your attention.
Thank you, Tamás. Are there any questions right here? No? There is one question. Okay. Yes. Let me start with this one and then yeah. Okay. How do you train the UTI to symbols? As I assume you didn't have the alignment between the image sequence and the symbols. Did you manually annotate the alignment?
I will go back to the question to read as well. Yes, so the UTI to symbol, which was the first step, image sequence and the symbols. No, actually we do have. So because this data was recorded in a way that we recorded both ultrasound and speech in parallel. So based on the speech data, we can do like forced alignment to know where the symbols are. Yes, I think that was the question about.
It was heard from the examples, because I'm Hungarian, that a lot of consonants are missing or are realized not a correct way. That do you plan or did you such kind of experiments that contain all the Hungarian speech sounds? Because if you do that, then you can go ahead. Because you will know which speech sounds are not correctly generated and which are tolerably good done.
Thank you very much for the question. Yes, of course, we would like to make sure that all of the Hungarian speech sounds are included. The problem is that in the ultrasound data, not all of the speech sounds can be recognized from that. Partly because there is also the lip information, so there is not everything in the ultrasound.
So, in fact, the contribution in the tachytron, the contribution of the encoder is like a wave to vec, is in fact to provide context so that you can recover words, phonetics, and so on, so complement with lip information and so on, so to have a better output. And after you have this attention model here that's somehow just complement with small, because the alignment is 1-to-1. You have as much frames of articulation than frames of sound. So it's just somehow complementing the misalignment, this asynchrony between articulation and sound. So are you planning to have an ablation study to understand what are the contribution of the encoder and the attention model to the quality of the synthesis?
Mm-hmm. Yes, of course, plans. We always have a lot of plans. Yes, this is something that we would like to do it in the future. Again, this was a study that during a lunch, Csapó and myself was talking about his current research, my current research, and we thought, okay, let's try to put these two together, and it seemed to work, and we don't have the next step yet.
Thank you. That concludes this session, and we will be back in about 15 minutes, I think, 3:20 local time. Okay, thanks.